Okay, but what's 1/10 squared? 1 over 100, right? 1 over 100. So this is going to be sum n equals 1 to infinity, 34 over 10, and then that's really 1 over 100 to the n. One-tenth squared is 100, 1 over 100. Now, finally, I've got an n here. And so I can do my little -1 plus 1 right there. I'm going to have to come back up here. So continuing, sum n equals 1 to infinity. All right, I have 34 over 10, and then I have 1 over 100, and then to the n, and here comes -1 plus 1. Sum n equals 1 to infinity, 34 over 10. Okay, I'm going to rewrite this as 1 over 100 to the what? N minus 1, and then what? Times 1 over 100 to the first power, which is just itself. What now? I'm almost there. Yeah, put these two together, right? Put those two together, and that's going to be your A, isn't it? And we will be there. Okay, so we are at 34 over 1,000, and then times 1 over 100 to the n minus 1. And we are finally geometric, right? We're finally a geometric series. We have A, R to the n minus 1. So A for us is 34 over 1,000. And then R for us is 1 over 100. And I hope it's obvious that the absolute value of that is less than 1, which means it converges, right? That is a convergent geometric series. Okay. Ready to go back here now? Okay, so this now becomes, so that decimal right there can be rewritten as, don't forget the part we ignored. We ignored that there was 2 plus 1 over 10 plus, now we converted that to sum n equals 1 to infinity of 34 over 1,000 times 1 over 100 to the n minus 1. We know that that is a convergent geometric series. And so we know that that converges to exactly, that whole thing converges to exactly A, 34 over 1,000, over 1 minus R, and R was 1 over 100. Right? That's what this became. This becomes this because it's convergent. And now I'm just going to clean up that complex fraction here. This is going to be 2 plus 1/10 plus 34 over 1,000 over 99 over 100. Right? You rewrite this 1 as 100 over 100, then subtract 1 over 100, you get 99 over 100. And then flip. I'm going to flip that. So when I flip it, get 100 up here, I get 99 down here. And what happens with that 100 and 1,000? Just reduces out, right? Becomes a 10 on the bottom. That's 1, and then this is 10. So you get 34 on the top, and what on the bottom? 990. So this now becomes 2 plus 1/10 plus 34 over 990. Almost there. Almost there. I need to put this together to be one fraction. So I need a common denominator between all of these. Remember, this 2 is a 2 over 1, right? So my common denominator is going to be 990. I need all of them have a denominator of 990. So that means I have to multiply top and bottom of this by 990. What's 2 times 990? Y'all better double check me here. What is it? 1860? 1960. What? 990 times 2? 1980. 1980. Okay, I trust you. 1980, that's me rewriting 2. Plus, how do we rewrite this? I need to multiply top and bottom by 99. So 99 on top, and then on the bottom 990. And then plus 34 over 990 equals, okay, you all have the same denominators. Denominators. So you add up the numerators. 2,113? There we go. Now, I'd like for you to take 2,113 divided by 990 on your calculator and tell me what decimal you get. Do you get 2.13434434? Okay. All decimals that repeat, all rational numbers can be rewritten as a fraction. All of them. But you just can't do it for like pi and other things like that. So anyone who's a math major, mostly just math majors see this. One of the first things that you do when you learn how to prove theorems, one of the first theorems you ever prove is to prove that the square root of 2 is not a fraction. You have to prove it. You have to prove why that's true. So what you do is you prove that by a method called, you prove it by contradiction. So you assume it is a fraction and then you contradict yourself. Anyways, we move on. This problem right here, a lot of calculators have a button that convert from decimal to fraction. The point of that exercise, I hope, is obvious in us going through it. There's a lot of things you have to understand and keep track of, right? So that is the type of problem that I do like to put on exams. Show this repeating decimal is a fraction. Find the fraction. Now, I will admit, the one I gave you is a little hard because there's a 1 here. If that 1 wasn't here, like if it was just 2.343434, it's a little bit easier problem because you don't wind up having to do as much of the algebra we had to do. And the problems in your homework, right, that you'll see in the book, don't have that additional number right in front of this. The pattern starts right away. See how it goes. All right, we got to move on. So I've been debating back and forth on the next topic here, and I still don't know what I'm going to do. My concern is that I'm not going to be able to get where I want to get in this class if I bog myself down in this next topic. And in the big scheme of things, it's not super important. So, all right. Let's do 8.2.15 first. This one we have to do, and it's very, very clean, very straightforward. So right now, we only know of one specific special series, right? There's only one series that we actually know what to do with. It's a geometric series. If I hand you a series right now and ask you, if I gave you a series right now and ask you, does this converge or does it diverge? The only thing you have right now is the nth term test, right? Remember the pregnancy test thing? We have that, but that only checks to see if it diverges, right? You take what's in here, you let it go to infinity, and you hope that it's something other than 0. The nth term test, and then other than that, the only other thing you have is you hope that it's a geometric series. Now we're going to look at a different series, okay? And the series, it's called a harmonic series. And it sounds kind of ugly. Harmonic sounds like this could get ugly, but it's actually very, very simple. A harmonic series is any series of this form. It's any series sum n equals 1 to infinity, where on top you have what? A constant, some number. Okay, let me give you a number. I'm going to give you a specific example here. 8. There's a constant, right? over, on the bottom, as long as what's on the bottom is some linear expression in the variable n, then it's harmonic. So I'm going to just write a linear expression here, 3n plus 1. Do you all agree 3n plus 1 is linear? It's not quadratic, doesn't have a square root or something like that, no trig functions. That's just a linear expression in n. Anytime you see this, it's called harmonic. And I gave you some other examples here. Look at all these. Do you all agree on each of those? You have a constant over linear. First one, constant 1. Linear expression, isn't n by itself linear? Right? The next one, 4 over linear expression. Next one, okay, it's negative 5. That's still a constant, right? Over n plus 5. Oops, what the hell? How did that happen? How did that happen? I typed CP by dragging my mouse. It must have been my macro in there. Did that. There we go. So that n plus 5 is linear, right? I've got great news. Got great news. What does it say? All harmonic series diverge. All of them. As soon as you know it's harmonic, you know it's over. All right? You don't have to do anything crazy. You just say it diverges. All right? Now, there's one thing you have to be careful with, all right? There's one little thing. Look at this right here. Would this be a harmonic series? Well, a constant on top, right? Linear on the bottom? But why is this not harmonic? Because you can't plug in n equals 1, right? What happens when you plug in 1? It's undefined. So there's a little catch. There's a little asterisk next to this. Your harmonic series has to be defined for every value of n in order for you to say it's harmonic. In all the examples I gave you, notice that the denominator would have never been 0. Like if you go back and look at all these, there's no n you could plug in and get 0. Let me give you one more of these. So this is not harmonic. Okay, this right here, what if I give you this? Sum n equals 1 to infinity. Let's go 3 over n minus a half. Is that harmonic? Is there any value of n you could plug in where this thing would be like undefined? If you plug in 1/2, right? But what are our n values going to be? 1, 2, 3, 4, 5, 6. They're never going to be that, right? It would have to be a whole number, right? So this would be harmonic, all right? This would be okay. This would diverge, all right? You would have to find where the sequence, yeah, you could say function, but where the sequence would be discontinuous or undefined. Now, I'm not going to try and trick you. I just can't sit up here and say that constant over linear always harmonic. I mean, there are some exceptions, right? Okay, so what I'd like to do now is see if I can prove to you why a harmonic series diverges. I want to prove to you why. Because it's not easy for everybody to I guess, accept this. Let's start with the most simple harmonic series there is. 1 over n. That's about as simple as it ever gets with a harmonic, right? Your constant on top is 1, and your linear expression is n. What I'm telling you is that this diverges. So let's write out the first few terms. If I plug in 1, I get 1 over 1 is 1. Plus, if I plug in 2, I get a half. Plus a third. Plus a fourth. Plus a fifth, right? And that keeps going forever and ever. And the question is, does this add up to be a number? Does it diverge or does it converge? I'm telling you it diverges, right? I would like to explain why though, right? So if somebody gave me this and I didn't know it was harmonic and I was trying to figure out if it converged or diverged, the first thing I would do is the nth term test, right? The pregnancy test. I would do the nth term or the test for divergence. I would take the limit as n goes to infinity of 1 over n, and what would I get? What's that limit equal to? 0. And what does the nth term test tell me when I get 0? It fails. So this tells me nothing. I promise you that on our final exam, somebody's going to tell me that this series goes to 0 because they don't understand that this test doesn't tell you anything. When you get 0 here, it doesn't tell you anything, right? But people will confuse that. So I try that, I look at that, I say, oh, that goes to 0, crap, I don't know anything else. Then I look at it and say, is it geometric? Is this a geometric series? Why not? What tells you this is not geometric? There's no n in the exponent, right? Geometric series, you have to have a times r to the n. The n has to be in the exponent. And I think on your sheet that has the series test, it even tells you that. On the side, there's like little comments, and it says something about this is good for exponential or something like that. What does this say? On the very far right column of geometric series.
Useful for comparison tests and term HDM series similar to HDR and last one.
Yeah, so, yeah, maybe it doesn't say as much as I thought it did. But the whole point is the n is in the exponent, right? That's when that geometric series is useful. Here, the n is not in the exponent. So this is not a geometric series. So we're stuck, right? But again, we're acting like we don't know this. So how do I prove to you that this is divergent? You ready for the proof? It's not a, like, mathematicians wouldn't call this a good proof, but it's good enough for this class, I think, for us to understand it. Okay, so I want to know what these add up to. I want to know what this adds up to be, right? I want to know what this adds up to be. So I'm going to see if I can convince you. Hopefully you'll agree. All right, I have to write a bunch of stuff down. Okay, 1 plus a half plus a third plus a fourth plus a fifth plus a sixth, sixth plus a seventh plus an eighth. I'm going all the way out to 16. Plus a ninth plus a 10th plus 11th plus a 12th plus a 13th plus a 14th plus a 15th plus a 16th plus forever, right? All right, that's what I want to know. That's what I want to know. What is this? All right, let's see if I can sell you on this. Do you believe this, that sum, whatever it is, must be bigger than the following? Okay, or I'll say bigger than or equal, all right? Bigger than or equal to the following. Do you believe that sum is bigger than just 1? Why? Well, that's 1, and then you're adding a bunch of stuff, right? So that sum is bigger than 1, yes? Okay. How about 1 plus a half? Well, that's just the first two of these, right? Those two together, that's this. So this is, I guess you could say, smaller than that, yes? Or you could say that's bigger than this. We still agree? Yeah? Okay, now this is where things start getting weird. What I'm going to do now is I'm going to take these two right here, okay? And I want you to think about this for a second. Which of these two is bigger? Is 1/3 bigger or 1/4? Which of those two numbers is bigger? 1/3. 1/3 is bigger than 1/4, right? So do you agree that if I add to this 1/4 twice, okay? So I have the 1 here, the 1/2. If I do, instead of 1/3, I did 1/4 and 1/4. Do you agree still that that's bigger? Bigger than this? Or is this smaller than this? Yes? Because one is 1, right? Half is a half. But 1/4 and 1/4 should be smaller than 1/3 and 1/4, shouldn't it? Yeah. And then you have all that other shit over there too. So that's definitely bigger than this, yes? Yeah? Okay. Now what I want you to do is look at the next, not 2, but the next 4. What's the smallest number in that list of 4 numbers? 1/5, 1/6, 1/7. What's the smallest number? 1/8. So do you agree still that if I add now 4 of these 1/8, if I do 1/8 4 times, I'm going to put it like this. So y'all agreed this is the same as this is the same as this. Y'all agreed that this right here is smaller than that, right? And y'all are hopefully agreeing that this is smaller than that. Because 1/5 is bigger than 1/8, 1/6 is bigger than 1/8, 1/7 is bigger than 1/8, and 1/8 is 1/8. So 4 of these 1/8s is definitely going to be smaller than that. Yeah? And I'm going to keep this idea. Now, let's see. First I took the first 2, then I took the next 4. What do you think I'm going to do next? Next 6, it's going to be 8. I'm going to take the next 8 of them. See those 8 numbers? I'm squaring each time. So what is the smallest number in that list? 1/16. So do you all agree that this list here is smaller than, if I did 1/16, how many times? 8 times. Five, 6, 7, 8. Okay? That right there. So this is smaller than that, isn't it? This is smaller than that. This is smaller than that. This is smaller than that. And these two are equal, right? So y'all still happy with this inequality I have here? That this is smaller than that? Now I'm going to take the next what? How many of them? I'm going to take the next 32 of them, right? I took 16 here. I took 16 of them here. I took 8 of, wait a minute, hold on. Sorry, I didn't. I messed up. I'm sorry. This was 8, right? This was 8. This was 4. I took 4 of them here. I took 2 of them here. Next would be 16. If you said 16, sorry. 16. If I take the next 16 of them, then I could do the same argument, couldn't I? I'd do the same argument. And then I do it over and over. And then I take the next, what, 32, then the next 64. And I could do that forever, couldn't I? Now, what can you tell me about this number right here? What is this number? Well, do that. What's that number? That's a half. What's this number? A half. What's this number? A half. And that's going to keep going, right? Forever? So what we're saying here is this. This right here equals this, right? What happens if I take 1 plus a half 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 forever? What do I get? Infinity. Right? These numbers are not getting smaller, are they? You could do the nth term test on this right here. What's happening to these numbers? They're not getting smaller, right? They're staying the same. They're converging to a half. They're not going to 0. So this is divergent, isn't it? It's becoming infinite. And what we're saying is the sum we're trying to find is bigger than that. And the only way to be bigger than infinity is to be infinity. And therefore, it diverges. So that is a rough proof of why harmonic series diverges, all right? Or just remember it does if you don't like it, okay? All harmonic series diverge. All right, now the next part. Damn it. I'm already halfway through class. Man, I always get so bogged down in this section. So all harmonic series diverge. It says here, I will prove this, and I just tried to. All right, telescopic collapsing series. This is the part I don't know if I want. You know what? I'm going to skip it. I'm going to skip it, all right? I might come back to this. If I have time at the end, I might come back to this. I mean the end as in at the end of chapter 8. We do not need this for any of the rest of chapter 8. This is a special type of series that behaves a certain way, but we're looking at the rest of class if we do this. And because it's not absolutely essential in this class or any class after this, I'm going to table it, all right? And move on. So now I want you to see some alternate notation for geometric series. So we already have seen this, right? This is we're wrapping up the section right now, so we're just kind of doing a little quick summary. We've already seen that notation, right? N equals 1 to infinity, a r to the n minus 1. And if we plug in values for n, this is the actual series that we get. A plus a times r plus a times r squared, blah, blah, blah. Keeps going. There's another notation where we don't have our index start at 1, but instead we start our index down here at 0, and we change the n minus 1, we change it to an n. That is an equivalent form of a geometric series. So if you see this, if you plug in n equals 0, then 1, then 2, you get the same exact sum. You get the same thing as if you start this with 1 and replace that with n minus 1. It's what we call a changing of the index. And when I first introduced sequences to you in 8.1, I always said n started at 1, right? So I'm now telling you that n can actually start wherever we want, all right? And sometimes we started at 0 instead of 1. And you'll see later on that this is actually going to become a convention to start at 0. But when you're first introducing sequences, we don't. We start at 1, all right? So if you ever see this, this would still follow the same thing. If the absolute value of r is less than 1, then this converges. It still converges to a over 1 minus r. So on your formula sheets or on that table of tests, is that on here? Is that on there? Sorry. Is that on there? I don't think this notation's on there. Can I see? Geometric.
No.
It's not. So where it has the geometric, I'm okay with you adding this in to your sheet. Okay, you can add this in there. It's just alternate notation. All right, last thing, and then we're going to be done with this section. So this is a theorem. This is a theorem. So when you have series, look at these formulas here. If I have a series, let me show you the two things first. Can we pull a constant? If we have a constant, can we pull constant out of a series? What do you think? If you have constants, can you pull constants out? Yes, you can. A way to think about it is this. If I were to give you this, this is 4 plus 8 plus 12 plus 16 forever, right? That's what that is? The question is, can I pull that 4 out? Can I pull the 4 out and just have the n here? Is that the same thing? It is, because this means you have the 4 and then you have the series. And if I do the series, I get 1 plus 2 plus 3 plus 4 plus forever. And if I distribute the 4 through, we get the original series up there. So constants can come out. The second property says that if you have a sum, and let's say you have two things together. What if I had 3 over 4 to the n? What is that? What kind of series is that? Geometric. Does it converge or diverge? Let me make it easier. There. Does that converge or diverge? Converges, right? Because r is 3/4, which is less than 1. This is a convergent geometric series. This second property says, what if I were to subtract from that this? Can you do this? Can you do this? Can you split this up into two different problems? Seems like you could, right? The question is, can you split that apart? Seems reasonable that you should be able to do this, yes? Okay, this is true, yes, but only if they are convergent. That means this is convergent, isn't it? That's convergent, and that's convergent, because they're both geometric series. This one has 3/4 as r, so that converges. This is 1/2 as r, that converges. As long as you have two convergent series, you can split them apart. You are not allowed to split them apart if they are divergent. In other words, if I had this, let's say I had that. Can you split that apart into two? What's that by itself? Geometric, convergent, right? What's this by itself? Harmonic, divergent. Can you split them apart? No. You're not allowed to, all right? You must leave them together. And then you'd have to figure out. So I just want to point out, right? This theorem says you can pull constants out and you can split series up so long as they are convergent. If they aren't convergent, you can't do it.
Is that the same with the constants? Or is the constant?
The constant's not as important, but you know, the constant should work no matter what. Okay, I'm moving on. We're done with this chapter. This section. 8.2. We're going to get into 8.3 now. All right, I'm going to read through this because it is important, all right? So we're going into 8.3, new section. This section is called the integral and comparison tests, which are on your sheets, on those little reference sheets you have, the table, right? So it says here, the main idea. So as we just discussed in 8.2, we can only find the actual sum of a convergent geometric series, right? Like if we have a geometric series and it's convergent, we can find the sum. It's a over 1 minus r. It also says we can find that if it's a convergent telescopic series, but we're skipping telescopic, so just ignore that. All right, so right now, we can only find the sum of a series if it's geometric and convergent. Generally, that's supposed to say finding. Generally, finding the sum of a convergent series is very difficult. So if I give you just some series, and it's convergent, and it's not geometric, finding the actual sum is really hard to do in general. All right? In this section, we're going to start using tests to determine whether or not a given series converges or diverges, and that's all we're going to be able to answer. It either converges or diverges, and that's it. We will not be able to find the sum, and that won't be our task. It's not our goal. That's not going to be our goal, all right? So how are we going to do it? Well, first thing is an idea that we need to understand, because I'm going to use it in just a second. And that is this. I'm going to write it. It's right there, but I'm going to write it. I want you to think about this. What if I tell you this? What if I give you, this is given to you, that you have some series, it starts at n equals 1, goes to infinity, and it's some sequence here, I don't know. What if I give you that and I tell you it's convergent? That means that when you add things up, you get a number, right? That's what you know. Then what can you tell me about this? Then does this converge? I want to hear your argument. So what's the difference between those two? The first one started at where? N equals 1. And this one's starting at 10, right? So this one is a sub 1 plus a sub 2 plus a sub 3 plus forever, right? And we know that that converges to some number, right? To some number. This one